questions on that one? Then let's come to the next one. So convert the following table. Oh, sorry. Didn't share the screen correctly. Convert the following table into the simplest algebraic form and draw the corresponding circuit. I don't know, maybe for 5 minutes, and then we are looking into that together as well. So let's look into that one as well. We have here the following truth table. Just check once. A, B. So now you can write here the formula. Epsilon is A naught B naught or A B. and that's nothing else than an XOR dot. So if you're drawing that, can you first? Then what you would have here is an XOR of A and B not. Or if you would draw it correctly, so if you would draw the DNF, that one here. It's like that. But if you're looking into the truth table of your XNOR, we never did the XOR. So, but that's the negotiated XOR. So here we have the XOR 0, 1, 1, 0. And here we have just the opposite of that, so 1, 0, 0, 1. Okay, and then there are different further problems we can look briefly through. We already did that one in the lecture, so analyze the following analog digital converting circuit. What happens if you put the voltage of 1 volt to UR and the voltage of 0.55 volts to UM? Note that UR is divided by the resistance into 0.25, 0.5, 0.75, and 1 volt at the 4 comparators and the negative inputs from the bottom to top. So what you have here is your reference voltage. You have here at the reference 1 volt, 0.75, 0.5, and 0.25 volt. And now you have at the input 0.55. And you have again the comparator. So 0.55 is smaller or is not larger than 1 volt. Therefore, that path is becoming true. 0.55 is not larger than 0.75. Therefore, that path is becoming true. 0.55 is larger than 0.5. Therefore, that one is getting true. And 0.55 is larger than 0.25. Therefore, that path is getting true. Now you have a 1 here, and that's it. So you have 1, 0 at the output. And now there is the same question for so here it's for 0.55, 0.76. So again, just here 1 volt, 0.75, 0.5, 0.25. And now at reference, we have 0.76. And again, so 0.76 is smaller than 1. It is larger than 0.765, larger than 0.5, and larger than 0.25. So therefore, this path is getting 1. And you have 1, 1 at the output. And the last one, 0.24. Again, 1, 0.75, 0.25, and 35, sorry. And 0.25. And you have here 0.24. So 0.24 is smaller than 1, smaller than 0.75, smaller than 0.5, and smaller than that. So you have 0, 0 at the output. 6 and 0.24. Yeah. No, here I did a mistake. No. But we already did in the lecture notes, there is an example on that as well. And the last one, there are two logic circuits, and you can try to analyze them a bit by your own. But my recommendation would be that you are doing that with this logically simulator, because what you have here is A and C as input. And you see that here we have an OR gate. So the output is 1 if A is 1. Output is 1. So that's mainly the inputs that we have here. Let's mark that a bit because it's a bit hard to see. That's A. And we have C as input. And yeah, that's it. And E is the output. And you see your input is directly the output. But now if the input is 0, the output stays 1, because you have there a feedback loop with a negotiated input to the B, and therefore it is due to the B keeping the 1 here. So what we have there is a way of how to realize an SR flip-flop. So that's a lecture as well. You remember in the lecture, we addressed that type of realization for an S-dominant SR latch with 2 OR gates. Here we have another one. So what you have there, maybe let me just rebuild that on the simulation tool with the 2 inputs. And we have there again OR. I will immediately share. Just 1 second.
Sir, I have a question on this one.
Yeah, go ahead.
Sir, here the output is dependent on E in some way, right?
The output is E.
Oh, so what about the path that is going down after A.
So here you have the output,
The
and that's
bottom
E.
one.
But there is a feedback loop to A again, and we will immediately see why. So let me just check if I did it correctly. Yes, then I will just reshare my screen. So that's exactly what we have here, okay? So the output is the lamp. I have the two inputs, A and C. I have here the OR. Well, it is working. So A, C, and the output. Now, if I'm turning on A, my input, my lamp is on. If I'm now turning off again, it stays on because I have here this feedback loop. You see? And now if I want to turn off again, I have to turn on the second input, and now it is off again. So that's nothing else than a set and a reset input. If both are 1, then it stays at set. So that's nothing else than an SR latch, but realized in a different manner. If the input is 1, the output is 1. And due to that feedback loop from the output again to the input, which is an OR, which has the negotiated reset input in the AND gate, it is staying here 1 because the output is 1 and the reset is false. Therefore, you have a 1 here as well. So now this loop is keeping the lamp alive. If you're now resetting here, then you will have here a 0 and the AND will become 0. Clear? And the same
Yes,
it is
sir.
for the second circuit. Just a minute, then I will rebuild that one as well. So we have here 2 OR gates and OR and 2 negotiation. And there. And the output is here. That. And now, if I'm turning on the set, then the lamp is on. Due to this double inverting. If I'm turning on the reset, then it's off. If I'm turning on both, then it stays off. So here I have now a reset dominant SR latch. The previous one was an S dominant. Here we have a reset dominant SR latch. So you can try to analyze the circuits directly as well, but to be honest, I also find it a bit hard if you're directly trying to analyze, because you have there the state of the previous circle in. So you have here A and B is the output, but it is an input as well. Now you can notate here the possible combinations for A and B to get E, but in reality, just the A and the D are the inputs. So if you have there this kind of feedback loops, then it's sometimes a bit hard to understand them, and then I would recommend to simulate them, to be honest. Okay, do you have any questions to these problems? Next week, we will then start with the last chapter about the machine code. So that's a very basic kind of programming where nearly all compilers are finally compiling their code into. And we will see a bit how a von Neumann PC is working. So most PCs are based on this von Neumann or Princeton architecture. And we will deal a bit with the commands and do some simple programming on paper where will try to analyze a bit how the sequence of a PC is working like. Then we are seeing each other on next Wednesday. Thank you for your attention and bye-bye.
Thank you, sir.
Sir,
Yes.
sir, for the exam, I've seen it like on the exam schedule. It's written it's open book.
No,
No, okay.
no. It is calculator only. Let me just share. Just 1 second. What are you studying? What's your program?
On my exam schedule, it's written that the exam is open book.
No. What is your program? What are you studying?
In this subject on informatics.
What is the program that you are studying?
No, I'm not having any problem in that.
You are not studying anything.
No, I am studying. I'm not understanding your question actually.
What are you
He
studying?
is asking about your degree
Course of study.
program.
Health informatics, industrial engineering, energy systems engineering.
Sir, I will email you. Maybe you will understand better that.
Let's look into together. What are you studying? I just want to know what you are studying. So what is
Oh, okay.
program?
I'm studying energy system engineering.
Energy systems engineering. Okay, then if you're going to the website of the PhD, then you are finding the section informations from A to Z, and there you are finding the exam schedules. I hope. I will just search the one. Energy systems engineering, and here. Oh, let me just share my screen. Here you are seeing the informatics for engineering, non-programmable calculator. Okay.
Okay, sir.
So maybe you have an older version, because in the very first version, it was an open book, but then we decided due to some complaints from the exam board and even in general, if it is an open book, usually the problems you have to solve are much more and you have much less time because somehow you have to prove that you are not just able to read, that you also understood the things. And therefore we opted for a non-programmable calculator as only allowed tool. And by that, the number of problems and the complexity of the problems will be different than for an open book exam. Any other questions? Then see you next week. Bye-bye.